All right, so we are looking at another linked list problem today. This is day 23, so we're like quarter way through, roughly, a little bit over a quarter, which is really exciting. About halfway through the semester, about a quarter way through the year, so fun stuff. Okay, so we are looking at remove node from end of linked list. Let's give it a read, and then we'll go for it. Okay, so you are given the beginning of a linked list head, which is just the first node in the list, and then also an integer n, and we want to remove the nth node from the end of the list and return the beginning of the list. They don't specify it here, but n is 1 indexed, so when we say like when n equals 1, for example, we want to remove the first node from the end of the list. So that would be the last node. 2 would be the second node, so the second to last node, and so on and so forth. Okay, so as far as what we mean by that, again, it looks like an array. It's not really an array, they're just representing it this way. We've got the nodes 1, 2, 3, and 4 with n equals 2. So we want to remove that guy right there, the one with the value 3. And so when we're done, when we detach that node, we want to kind of hook the left side up to the right side. And so the resulting list, if we traverse it, looks like 1, 2, skip 3, and go straight to 4. Okay, some edge cases that they give us. If we have just one node and n equals 1, then we'll just return nothing. Similarly, well, this is actually the same as the previous one technically, but if our list was just 1 followed by 2 and we want to remove the second to last one, that's going to be this guy right here. And in that case, we are just going to return 2. So in terms of linked list, and we'll talk about how to kind of do this in the code, but if we're removing something from the middle of the list, or the end of the list for that matter, we basically just need to hook up the thing before it to the thing after it. So if we're removing the last node, like we would just point 3 at none, right? Which is already, what we would get if we skipped over. So that's the case if we're trying to remove from the middle or the end. And then if we want to remove from the beginning, there's not really a before, like we can't hook nothing up to 2. So in that case, we would basically just remove this, or we could just consider the second node like the head of the list. Yeah. Okay, so some constraints they do give us just to make our lives a little bit easier here. The number of the nodes in the list is size. We're not given that, but they're going to call it that for the constraints here. And they tell us that size will be between 1 and 30, so the actual number of nodes is roughly 30, or no more than 30. And there will be at least one node is the other clarification they give us. The values of the nodes, which we're not going to manipulate, are between 0 and 100. And then n, which is like the index from the end that we want to remove, is between 1 and size. So that we'll always have a valid n. It's not going to be like 10 nodes and n is 15, for example. All right, and as usual with linked lists, there is a O of n space version of this solution, and then a more optimized O of 1 space, and we'll talk about both of them because they're pretty quick, and we've covered lots of linked lists before. So let's take a look. We'll go with an example, a somewhat short example list here, and then we'll tackle a couple of edge cases. So if our linked list looks something like this, 0, 1, 2, 3, let's say. Okay. One thing we could do is literally put these in a list, and that would let us kind of ascertain ahead of time what the size of the list is, right? Again, in the constraints, they tell us, hey, we're going to talk about the size. We don't know the size off the bat, and the only way to find the size at all is going to be to traverse the list. Which I didn't really think about that, but I guess you could do that. And then, okay, actually, so maybe we have 3 solutions to look at today. Anyways, if we decide to use O of n extra space, hello, welcome in. We are looking at remove nth node from the end of linked list. Give it a read if you haven't. Okay, so what we could do for extra space is we could just store these guys in a list like this. This is going to let us say, hey, actually, now we know what nodes are in the list. And once we have, so assuming we take this approach, and we know now that the length is 4 rather, for example, and let's say n is, what's an interesting example here? Maybe we'll say n is 2 in this case. All we have to do here is go to, well, okay, first of all, we know in this case that that means the node we want to remove is this guy. We just count the second one from the end, right? So if we wanted to know what the index that we were trying to remove was, we could say that it's just like the length. So we want to remove the one at length minus n. Okay. Now the problem is when we want to actually remove a node from a linked list, it's not sufficient for us to just kind of remove it from the array. The array is just referencing certain nodes in the list, right? The problem is that they're pointing in places we don't want them to point if we're trying to remove that node, right? So what we really need is for the node at length minus n minus 1 to point at the node at length minus n plus 1. We need this guy to point at that guy. And that is kind of equivalent to removing that node. I guess in terms of the actual nodes here, what we would do is we would say, you're no longer valid. Let's make this go like that. And this would produce the list 0, 1, 3, which is exactly what we want. The 2 is still pointing at 3, which is like, there's not really a real issue with that. We're removing the node anyways. So the linked list looks like what we want it to look like if we just take that previous node and point it at the following node. Okay, so is this ever going to cause us problems? I think because of the validity of like n and everything, the only issue that we would have to deal with is like if we wanted to remove the head node, we can't, like it's at index 0, so this would be a problem, right? This would take us to index -1 and then we'd be like, that's not really a node, right? So assuming we go with this version, the only edge case we need to account for is, hey, if this, so a little edge case scenario here, we'd say if length minus n is 0, then all we need to do is return head.next. Right? We would basically just say, hey, forget about this node. This is the rest of the list right here. Okay, so this would be if we had, for example, n equals 4 here. So if the last index that we want is the same as the length, then we're trying to cut off the first node, we can just return the next node. So pretty straightforward to do it this way. Again, the weakness or the major weakness here is that it takes extra space, but let's give it a shot in the code just because it pays to know a few different ways to solve a problem. So what could we do here? We could say, as usual, node list is going to be something like that. Okay, and I'll say current equals head. And we'll say while current node list dot append current, and current equals current dot next. So this is, we've done this quite a few times. This is kind of our idiomatic way of traversing the list and storing each node in the next index. Okay, once we got them all in the list, what do we need to find? Let's split view this so we can talk about this in the context of the calculations we just wrote. We need to remove length minus n, which means we need, for this set of pointers to change, right? Or this particular pointer needs to change. Let's preface this with, okay, let's say if the length of node list, which we now have because we've stored it in an array, or stored each node in an array, equals n, then we can just return head.next. And otherwise, what are we going to do? We'll say node list len node list minus n minus 1 dot next equals node list len. This is a little bit ugly. In a different world, I probably would have like stored this as a variable first, but that's okay. So we say, hey, go ahead and take the node before, hook it up to the node after, and then we can return head. Okay, let's see if that worked. Great, and we'll go for the submit just to make sure. Oh. Blah, blah, blah. Oh, okay, so here's the problem. If we're talking about the end of the list, this is also going to cause an index error. So if we're trying to remove the last node, then this node is not actually there. So here's what we'll do instead, is we'll say the previous node will be hooked up to the next node. So we'll do node list, len node list minus n. So the one that we're trying to remove, we want that guy's next pointer. So this way we can still refer to the none that's at the end without having to like use an index for it. Another way we could do this is we could just say like, let's add on a none node at the end. That's going to make us do some weird things with like the indexes though. So I think this is probably a better way to do it. And let's just make sure that actually solved our problem here. Great, that does it. So yeah, the only problem is like the none that the last node points at is not actually a node in the list. You could either add a none node and then adjust your indexes because the length is now one more than it was before, or you could just say, hey, like it's there, we can point at the none if we want, it's just we can't access it by index, right? And this also is still going to work for all of the middle or beginning nodes, or yeah, all the middle nodes. The beginning node is handled by this chunk right here. Okay, so this is the extra space version, but we could do it in a couple other ways. We could go all the way through the list and get the count, like we could get the size independently, and then we could basically do this without using indexes. We could say, for example, like in order to make this connection, we need to take this many steps, right? So instead of going directly to the index, we could traverse the list, get a size, go, X number of steps forward until we know we're at the node that we want to like disconnect, or we're right before the node that's going to be removed, and then we can do the same process. So what would that look like? Basically the same thing, it's just we would calculate this independently, I think, and then we would have to do like another traversal right here. So let's just take a look. We could say, instead of actually storing them, we could say list len equals 0. And then while current, we would say, instead of appending, we can just say list len plus equals 1. Okay, and then right here, we could say if list len is n, we return head.next. So this is capturing the same scenario, it's just we aren't actually storing the nodes this time. Okay, and then here's where it gets a little bit trickier, is for this section, we can no longer refer to the nodes by index. Instead, we could say something like, well, I guess we'll call it current again. Current equals head. And then we'll say like for, we could say I or whatever. I'll use the underscore to say like, we don't actually need this number, we're just doing a counter. So for underscore in range, list len minus n minus 1. So how many steps do we need to take? Well, okay, well, hold on, let's think about this. We still want to say, yeah, okay, if list len equals n, and then for blank in range list len minus n minus 1. Is that correct? So in this example, the list length is 4. We subtract 2. And then we subtract 1. Yeah, I think this takes us where we need to go. So we'll say current equals current.next. Okay, now we'll be at the position of the node right before the one that we want to remove. So we could say now current.next equals current.next.next. And then we'll return head. So this is another way we can do it without actually storing the nodes. We just traverse once to get the list length. And then we can use the list length and the index that we want to remove and some like arithmetic to figure out how to stop at the place that we want to stop, right? So this is O of n runtime, which is quite nice, but we don't need the extra space. And then we'll talk about one other approach. Assuming this worked, we might have some fixes to do here. Okay, that looks good, and that looks good. Okay, so another way to do it here. At the very worst case scenario here, we'll have to walk the list twice. So the question would be, could we just walk the list once and get a solution that way? And this is actually a pretty common like pointer or linked list like idiom, so I think important to know this. What we could do is just use a sentinel node, is what it's often referred to as. So let me do a little erasure here. Oh, hey, welcome in, VP. Let me do a little erasing, and then let's take a look. Okay, so the idea of a sentinel node is we can have another node that tracks kind of how far we are from the end of the list. And what I mean by this is like, so let's say, similar situation as before, we want n to be 2. We want to remove the second to last node from the end of the list. Let me clear my throat real quick. Oh my gosh, wait, I just read the message and understood what it meant. Hello, VPBF. Okay, so we could use a sentinel node, and so what I mean by this is we know where we want to end up, right? We want to end up in such a position that like our current or our traveler node, our traversal node is right here, right? And if we know that n equals 2, what we can do is, thinking about the end result here, we would like for there to be some other pointer that detects where the end of the list is, right? Well, where should that be positioned? As you can see, it's just positioned like n steps ahead, right? So pretty easy to detect the end of the list. Instead of walking the whole list and then walking again, what we can do is we can just set them up at the distance that we want them to be, and then just step them forward together. So if we initialized these pointers this way, or we set them up so that we had them at this distance, no matter how long this list was, we would very quickly be able to detect what is, in this case, 3 nodes from the end, so that we can remove the second node from the end. So yeah, and that's pretty much it. That's like we'll code through it, but that's kind of the overall solution. Couple edge cases that we want to handle that are similar to the ones we've already seen. If we are trying to, well, let's talk about one that isn't an edge case. If we want to remove the last node, that's totally fine. We'll still be in a position to do so. It's just we need to be careful about the code that we use. We can't, well, actually, no, we're just using the linked list, so it's pretty straightforward. We still want to hook up this guy's next pointer to like next.next, right? It's none, but that's fine. It's allowed to be none. So that's not an edge case. Here is an edge case, though. If this is the size of the list, then we'll have to handle one extra thing. So if you think about this, if n equals 4, we'll step that sentinel pointer ahead by 1, 2, 3, 4. And basically, we want to just check, because we're going to return a different thing if this is the case. We want to check that if this guy is still... No. That's not a good way for us to check, because this guy's going to start at the beginning anyways. If this goes to none immediately, we know that we're trying to remove the first element, right? Because we traversed the whole list and got to the end, but we went past the end even. So if the sentinel is pointing at none once we've set it up, then we know we're just trying to return the next node, right? Not the original head, but the next node after that. Okay, yeah, sentinel node's pretty straightforward to understand. Very, very useful in practice. Let's give it code here. We'll say current and sentinel equals head and head. Say for, again, I'll use the underscore to say, like, I'm not going to use this index, I just need to count. So for blank in range n, get a colon there, sentinel equals sentinel.next. Okay, so move it forward by whatever n is so that we can have it detect where the end of the list is. And then while, say, sentinel.next, sentens. Love that. Okay. Okay, well, sentinel.next, we're going to move both of them forward. So current equals current.next, sentinel equals sentinelly, sentinel equals sentinel.next. I miss Cornelli. Okay, and then by this point, we've gotten the sentinel to the end of the list. So this is going to stop when the sentinel is like the last node of the list. Or if we're trying to remove the first node, we'll be able to detect at this point. If not Sentinel, we can just return. Ooh, return head.next. Okay, otherwise though, what do we want to do? We'll say current, which is at this point positioned right before the node that we want to remove. Current.next is now going to be current.next.next. And now we'll just return head. Okay, I think that does it. Let's find out. Oh, just kidding. I was supposed to check this up here. I incorrectly said that this is the point where we'll be able to detect. We actually want to check immediately once we've moved that Sentinel node over. If it hits none right off the bat, then we know we're trying to remove the first node. We can just return head.next. And then once we know that we can actually go somewhere with it, we'll go ahead and move both the current and the Sentinel over. Okay, so same logic otherwise. And there we go. There we go. Look how many times I failed this back in the day. I wonder what I was doing wrong. Anyways, oh, failed it very recently. Oh, just kidding. Wait, was this just now? What? Is it the 27th today? Well, oh yeah. I did fail it because earlier when we did the extra space version, I did some weird stuff with indexes. Anyways, that's about it. So in terms of time-space complexity, our last solution here is still O of n time, because we have to potentially traverse the whole list once. O of 1 space, just like before. But I think important detail here, it's going to run twice as fast as the previous solution, right? So even though it's the same time complexity, which is a great place to be in, if we're choosing between something that runs in 10 seconds and something that runs in 5 seconds, that's still like a tangible difference, right? So time complexity isn't everything. We also have to worry about things like overhead and constants, coefficients, right? So in this case, this really is the optimal solution, although it's the same time and space complexity as the previous solution. Great. And that's it. We got 3 solutions in today. Fun stuff. Well, you guys already know this, but general body meeting tomorrow in the spa building at 7. So if you're tuning in tomorrow, the daily problem will be at 6. And we're going to give away a Labubu blind box. I think what we're going to do is, yes, Labubu, courtesy of VP's sister, who we purchased it from. Maybe what we'll do is like, if you, for every problem from the list we provide that you complete, like there with us, you get like an entry ticket for the Labubu, maybe. I don't know, we'll figure it out. Anyways, see you guys tomorrow. Bye-bye.